Welcome back to Everyday Nuggets. Light-emitting diodes, or LEDs, have revolutionized the way we illuminate our world. These small but powerful devices are everywhere, from the indicator lights on your electronics to the headlights in your car, and even lighting up entire buildings and cities. But have you ever stopped to consider what goes into making these tiny giants of illumination? The LED might seem like a simple technology. Still, its creation involves a fascinating blend of physics, chemistry, and precision engineering. These remarkable devices convert electricity directly into light, without the heat and energy waste of traditional bulbs, making them among the most significant lighting innovations of our time. Today, we're going to pull back the curtain on LED manufacturing. This process combines cutting-edge semiconductor technology with meticulous assembly techniques to create lights that last for decades. Let's embark on this illuminating journey to understand how LEDs go from raw materials to the finished products that brighten our lives. Before we dive into manufacturing, it's essential to understand what an LED actually is. At its heart, an LED is a specialized type of semiconductor diode. Unlike regular diodes, which control electrical current, LEDs are designed to emit light when an electric current passes through them. The magic happens at what's called a p-n junction, where two differently treated semiconductor materials meet. When electricity flows across this junction from the negative N side to the positive P side, electrons and electron holes recombine. This recombination releases energy in the form of photons, light particles. The color of the light depends on the specific semiconductor materials used and the energy gap between their conduction bands. What makes this process so efficient? Unlike incandescent bulbs that waste energy as heat, LEDs convert electrical energy directly into light. This fundamental difference is why LEDs use up to 75 to 80% less energy on average than traditional lighting, while lasting up to 25 times longer. The journey of an LED begins with its raw materials, primarily semiconductor compounds. While the first LEDs were made from gallium arsenide phosphide, GaAsP, which produces red light, today's LEDs use a variety of semiconductor compounds to create different colors. The most common materials include gallium arsenide, gallium phosphide, gallium arsenide phosphide, silicon carbide, gallium nitride, indium gallium nitride. The breakthrough that enabled today's bright white LEDs came with the development of gallium nitride technology. By combining a blue LED chip with a yellow phosphor coating, manufacturers could create LEDs that appear white to the human eye, a discovery so significant that it earned the Nobel Prize in Physics in 2014. Beyond semiconductor materials, LED production requires various metals for electrical contacts and leads, typically copper or aluminum, as well as protective packaging materials, such as epoxy resin, that encapsulate and protect the delicate internal components. These raw materials are processed in ultra-clean facilities, where even microscopic contaminants could ruin the final product. The semiconductor industry maintains clean rooms that are thousands of times cleaner than a hospital operating room, with workers wearing specialized bunny suits to prevent contamination. The journey from these raw elements to the finished LED is a testament to human ingenuity and precision engineering, involving multiple complex stages that we'll explore in the next section of our video. Inside specialized manufacturing facilities, LED chips are grown layer by layer using a process called MOCVD, metal organic chemical vapor deposition. It starts with a sapphire wafer, essentially a thin disc made of crystalline material that's heated to about 1,000 degrees Celsius, roughly as hot as a pizza oven at maximum temperature. Gaseous chemicals containing gallium, indium, and other elements are then blown into the chamber, where they decompose and adhere to the hot wafer, forming fragile semiconductor layers. The most critical layer is the active region, which is thinner than a human hair and contains special ultra-thin quantum wells where electrons recombine to produce light. By carefully controlling the ratio of indium to gallium in these wells, manufacturers can dial in exactly which color of light the LED emits. Once the layers are complete, the wafer is cut into thousands of individual chips using diamond saws, and each chip is tested and sorted by brightness and color to ensure consistency. This entire process, from raw materials to finished chips, requires extreme precision. Still, it's what allows LEDs to be mass-produced efficiently and reliably. Now that we've covered how the crucial LED chips are manufactured, let's examine how these tiny electronic components become the finished products we use every day. Assembly processes vary significantly depending on the final application, but most follow similar fundamental steps. For standard LED light bulbs, the journey begins with mounting the LED chips onto a circuit board. The chips are carefully placed using automated pick-and-place machines that ensure precise positioning. These machines can put thousands of components per hour with remarkable accuracy. Once positioned, the LED chips are soldered to the circuit board using reflow soldering, where the entire assembly passes through a controlled heating process that melts solder paste to create permanent electrical connections. This creates what's known as an LED module, the heart of any LED lighting product. Next comes the integration of control circuitry. Unlike traditional incandescent bulbs, which connect directly to AC power, LEDs require drivers that convert AC power to the DC power they need. These drivers also regulate the current to protect the LEDs from power fluctuations and ensure consistent light output. Without these drivers, the LEDs would quickly burn out or function erratically. Have you ever wondered why LED bulbs have those distinctive heat sinks? Unlike incandescent bulbs, which release most of their energy as heat, LEDs are much more efficient, but they still produce some heat that must be managed. The heat sink, usually made of aluminum, draws heat away from the sensitive LED components through thermal conduction, then disperses it into the surrounding air. Proper thermal management is crucial for maintaining the long lifespan LEDs are famous for. The final assembly includes adding a diffuser, that translucent cover that spreads the light evenly and protects the internal components, and the base that connects to your light fixture. The entire assembly is then tested for proper function, light output, color accuracy, and safety before being packaged for distribution. LEDs have revolutionized far more than just our light bulbs. Their versatility has enabled applications that were previously impossible with older lighting technologies. One of the most visible applications is in displays. Every pixel in your smartphone, computer monitor, or modern TV likely contains multiple tiny LEDs. These displays use RGB LED arrays, combining red, green, and blue light at varying intensities to create millions of colors. The latest technology in this field is micro-LED displays, in which the individual LED elements are shrunk to microscopic sizes, enabling incredible resolution and contrast ratios that outperform even OLED technology. Bright lighting represents another innovative application, pairing LEDs with wireless connectivity and control systems. These systems allow users to adjust brightness and color, and even program lighting schedules from their smartphones or voice assistants. The digital nature of LED technology enables this level of precise control, creating opportunities for both energy savings and enhanced user experiences. In agriculture, specialized LEDs are transforming how we grow food. By tuning the specific wavelengths of light, LED grow lights can be optimized for different stages of plant growth. Some wavelengths encourage vegetative growth, while others promote flowering and fruiting. This precise control enables year-round indoor farming with significantly lower energy costs than traditional growing methods. The automotive industry has embraced LEDs not just for their efficiency, but also for their design flexibility. Modern vehicles feature LED headlights, taillights, interior lighting, and even dynamic light displays. LEDs' quick response time also makes them ideal for brake lights, where the milliseconds of faster illumination can translate into feet of reduced stopping distance in emergency situations. LED technology continues to evolve at a remarkable pace. Researchers are working on increasing efficiency even further, with some experimental LEDs approaching theoretical maximum efficiency limits. New materials and manufacturing techniques promise to make LEDs even more affordable, while opening up new applications we haven't yet imagined. Thank you for watching another episode of Everyday Nuggets. If you enjoyed this episode, please like and subscribe for more videos. If you have suggestions for other everyday things you'd like to learn about, please leave them in the comments below. Stay curious.